Okay, yes. Okay. Yeah, thanks very much for coming. Today I will talk about a recent work with Ashley Montanaro. It is about quantum communication complexity of linear regression problem. As you know, quantum computers are designed to solve some problems much faster than classical computers. And so far, we have many of these kinds of examples. And for example, maybe quantum computers could be good at solving linear algebra problems. And a very fundamental problem is a linear system problem. In this problem, we assume we are given some quantum access to a matrix A, and we also assume we have the ability to prepare the quantum state B. Our goal is to prepare the quantum state of A inverse B. So this is a solution of the linear regression problem. Here, A inverse means the pseudo inverse if it is not invertible. About this problem, the first breakthrough was due to Harrell, Hastings, and Loyal in 2008, and after that, there were many improvements. Basically, the result says there is a quantum algorithm that can solve this problem in complexity, kappa times pi log in the dimension, and also pi log in the 1 over epsilon in the accuracy. Yeah, this is quite important since it's only pi log in the dimension, and usually kappa is the condition number. Because of the wide applications of the linear system problem, this algorithm leads to many applications in many areas, especially in machine learning. For example, the efficient quantum algorithms for the recommendation system problem proposed by Karnidis and Prakash. However, in 2018, a graduate student, Evan Tan, showed that classically, if we use some special data structures similar to the QRAM, then there is a classical algorithm that can also solve the recommendation system problem in time pi log in the dimension. So this is very impressive since maybe we saw pi log in the dimension is a quantum thing, but now you see classically we can also achieve this. So this basically means no exponential speedup for this recommendation system problem. And indeed, you can also use Tan's technique to propose some other classical algorithms for some other machine learning problems, especially usually in the low rank case. And this means for those problems, no exponential quantum speedups. And these algorithms are known as quantum-inspired classical algorithms. When we explore quantum speedups, usually we are interested in three complexities: the time complexity, the query complexity, and the communication complexity. The quantum-inspired classical algorithm says no exponential speedup. Usually, this is with respect to the time and query complexity. So, maybe we wonder how about the communication complexity. And in this talk, the main result I want to tell you is that in terms of the communication complexity, quantum computers can have exponential speedups for some fundamental linear algebra problems. Yeah. Okay, maybe the first question is what is the communication complexity? I will give a very high-level introduction about communication complexity. Okay, let's start from the classical case. Suppose we have a Boolean function f, and Alice has an input x, and Bob has another input y, but they want to compute fxy. So you see, they have to do this together. They need to communicate, since Alice don't know y and Bob don't know x. So the cost used in the communication is called the communication complexity. And this complexity is counted by the number of bits of the information used in the communication. For example, Alice can just send x to Bob, so Bob knows everything, and so Bob can compute fxy. By doing this, you see x has n bits, so by doing this, the complexity is odd n. But maybe for some problems, they can do better than odd n. And this picture describes a very practical protocol for them to compute fxy. In the first round, Alice does some local calculation and then sends something to Bob. And after that, Bob does some other local calculation and sends something back to Alice, and so on. So at the end of this protocol, let's say Bob can compute fxy. In communication complexity, usually we do not care about the local cost. That is, the cost of the calculations did by Alice or Bob independently. So we usually assume Alice and Bob have unlimited computational powers. So, they can do any kinds of calculation very efficiently. And the communication, can be one-way or two-way. So this is quite obvious. One-way means only Alice can send information to Bob, or the other way around. And two-way means they can send information to each other. In the quantum case, the situation is very similar. Now we assume they can send quantum information to each other. Basically, we mean the quantum states. And the quantum communication complexity is counted by the number of qubits used in the communication. Okay, this is a very high-level introduction about the communication complexity. Now let's come back to the problem we care about, the linear regression problem. This is a two-part case. Let's say Alice has a matrix m times n, and Bob has a vector. Now they want to solve this kind of linear regression problem. And more precisely, the task is, in the quantum case, they want to output the quantum state of A inverse B up to some error. And in the classical case, to allow for a fair comparison, we don't need them to output a vector solution. They only need to output some samples from a distribution close to the one defined by this quantum state. So you see, this classical task is indeed a little weaker than the quantum one. One more thing I want to say is, for simplicity, we assume the entries of A and B are specified by power log mn bits. Here mn are the dimensions, since we want to know more about the complexity in terms of the dimension. Okay, this is the problem. So about this problem, our results are summarized in this table. Here, this one-side error means the communication is one-way, and two-side error means it is two-way communication. And the kappa is the condition number of A. So if the communication is from one-way from Alice to Bob, then you can find a quantum protocol such that the communication complexity is kappa squared times this mean m and n up to some power log factors. And you can also prove a law bound. You see, it means this mean cannot be improved. And classically, the naive protocol is just Alice sends the whole matrix to Bob. So the up bound is m times n, and the lower bound is also mean mn. So in this case, as you can see, even if kappa is order 1, the quantum speedup is at most quadratic. But the results are much better in these two cases. If the communication is from Bob to Alice, then you can find a quantum protocol such that the communication complexity is kappa squared up to some power log factors, and the lower bound is kappa squared. So basically, this means this protocol is very close to optimal. And classically, the up bound is odd m, and the lower bound is this mean. The result is similar in the two-way communication case, except that it is linear in the condition number. And an interesting thing about the results is that all these lower bounds hold even if mn are equal to each other and kappa is order 1. So this means, for well-conditional linear regression problem, in these two cases, quantum computer do have exponential speedups. Okay, this is the main results. So next, I will show some details how we obtained this table. Okay, first, the quantum protocol. And you will see the quantum protocol is indeed very straightforward. I will give an example. The communication is one way from Bob to Alice. Since Bob has a vector, so he can prepare the quantum state of this vector B. So he sends this quantum state to Alice. Alice has a matrix A, and she needs to apply A inverse to this state. To do this, she constructs a unitary of this block form. This top left corner is A inverse divided by the operator norm. Then she applies this unitary to the state. And, and this state is basically what she wants, since you see this first one contains the information of A inverse B. So what she needs to do next is to just measure this state, and the success probability is at least 1 over kappa squared. So this means that Bob has to send kappa squared copies of the state to Alice. You see, since B is a vector of dimension m, so this state contains 1 plus log m qubits. And so in total, this quantum protocol uses kappa squared log m qubits. So this is a quantum protocol. Yeah, it's pretty straightforward, but you will see this protocol is indeed very close to optimal. So you need to prove some law bounds. Yeah, we will use the harness of the disjointness problem. In this problem, Alice has a n bit string x, and Bob has another bit string y. Now they want to determine if there is a I such that xi and yi are both 1. So basically, they want to find something in common. About this problem, there are some knowing results. In the quantum case, if the communication is one-way, then the communication complexity is odd n. If it is two-way, then it is the root of n. But classically, it is always odd n. So we will use this result to prove a law bound. So we need to do some reduction. Since Alice has an n bit string x, so she can construct a diagonal matrix A. And this diagonal entry ARR is 1 if xi is 1. Otherwise, it is 1 over some epsilon. Epsilon is a very small parameter. And Bob can find another vector similarly. If 1i is 1, then bi is 1. Otherwise, it is epsilon. Since this linear system is diagonal, so the solution is very easy to figure out. The ith entry of the solution is 1 if both xi and yi are 1. If only xi is 1 or only 1i is 1, then it is epsilon. Otherwise, it is epsilon squared. So this is the first case is the case we care about. Okay, let's denote the first case as P and the second case as Q. Then in the quantum state form, the solution has this kind of expression. Okay, now let's choose a very small epsilon. It is 1 over root of n. Okay, the disjointness problem is hard even if the size of P is at most 1. So as you can imagine, if P has just one index and epsilon is very small, and suppose there is a quantum protocol for Alice and Bob to prepare this quantum state, then they can measure this quantum state. And since epsilon is small, so when they measure state, with a very high, with large probability, they will see the index from P. And yeah, this probability is very close to a half. Of course, they don't know what is this P, but what they know is if they measure this state many times, they will see the same index many times. This index from basically from P. But on the other hand, if the P is empty, so we don't have this term, and this is basically very close to a uniform superposition of the indices from Q. So when they measure, of course, for the disjointness problem, you can assume Q is large. Otherwise, the disjointness problem is trivial. So when they measure this state, they will see different indices from Q almost uniformly. So you see these two results are different. So from these two results, Alice and Bob can distinguish which is the case, and so they can solve the disjointness problem. So this is a reduction. So this means that if they can solve the linear regression problem, then they can solve the disjointness problem. But the disjointness problem is hard. So we can use the bounds for the disjointness problem to obtain the bounds I claimed in the table. So this is the basic idea of the proof. Okay, next I will focus on more general case, the multi-party case. Now we assume there are S players. Each player PR has a matrix and a vector BI. Now they want to solve this kind of linear regression problem. And A and B have this block form. In the multi-party case, you should be very careful since there are many different models you can use. In this talk, I will focus on this quantum coordinate model. It is similar. It is similar to the classical coordinate model. We assume there is a referee R such that the communication is between Pi and R. So you see, so basically, for example, if P1 want to send some information to P2, P1 has to send the information to the referee first, then the referee sends the information to P2. So basically, they can communicate with each other. And the task is similar. Here we here we ask the referee to output the quantum state in the quantum case, and classically the referee has to output some samples. So the task is similar to the previous one. About this result, about this problem, our result is summarized in this table. In the quantum case, you can find a quantum protocol such that the communication complexity is s to the 1.5 times kappa. And when we explore quantum speedups, we care about the classical law bound. It is s times n. N is a dimension. So if let's say if s is small and kappa is small, then quantum computer can have exponential speedups. In the following, I will mainly focus on this quantum upbound, this quantum protocol. And the main technique is quantum single value transformation. Quantum single value transformation is a very powerful technique for designing quantum algorithms. It says, suppose you have a Hermitian matrix and a unitary of this block form. This top left corner is A over some alpha. And f is a bounded polynomial of degree d. Then QSVT tells you that there is a quantum circuit that implements this kind of unitary. This top left corner is f a or alpha. It is a polynomial of this matrix. And this unitary uses all the applications of U and U dagger and some other simple gates. So one direct application of this result is, you can prepare this quantum state. One result we proved is that in the quantum coordinate model, there is a quantum protocol for the referee to use this unitary, and the communication complexity is SD log n. Basically, this result says in the quantum coordinate model, you can still use QSVT. Since QSVT is used for technical, so you can use this result to propose some efficient quantum protocols for some problems. Okay, let's say the linear regression problem. Now you need a polynomial approximation of X inverse, and by the QSVT, you can find a quantum protocol such that the communication complexity is s to the 1.5 times kappa. One simple way to see this is, maybe we compare it with the time complexity. When we use QSVT to solve linear regression, the time complexity is TA alpha divided by the sigma mean. Sigma mean is the minimal non-zero single value of A. And the TA is the complexity of constructing this unitary. So alpha is a normalization parameter. Indeed, for communication complexity, you can still use this formula. And you can also compute this TA is just S log n. Of course, here TA should be understood as communication complexity. And alpha is this quantity. So this gives S to the 1.5 times kappa. As you can see, there is a big difference between time complexity and the linear time complexity and communication complexity. Usually, in time complexity, it's quite hard to compute TA and alpha. But for communication complexity, you can compute these quantities precisely. Okay, I think I will skip this second application, the Hamilton simulation. You can also do Hamilton simulation. Basically, this is the communication complexity. Okay, finally, I'll make a simple conclusion. The QSVT is very useful technique, but unfortunately, it can be dequantized. So this means when you use this technique to propose quantum algorithms, you may not have exponential speedups in terms of time and query complexity. But in the quantum coordinate model, you can still use QSVT. So this means you can find some efficient quantum protocols for some problems. So I think this means for some problems where quantum computer lose exponential speedups in terms of time and query complexity, it is possible to have exponential speedups in terms of communication complexity. So of course, it is interesting to explore more, but you need to prove it is classically hard. Okay, one more word. Bristol is hiring postdocs, so if you have any interest, please feel free to contact Ashley Montanaro. The salary is very good. Okay, thanks very much for your attention.
Changpeng for the really nice talk and the nice results. I'm sure there are some questions, and just a reminder that if everyone could keep their seats for the question period, and then in 5 minutes you can switch rooms.
Sorry, thank you for the very interesting talk, and sorry for a very dumb question. On page 11,
11.
on page 11, yeah, I'm just wondering what's the actual zero state for? Is it an ancilla qubit or something?
Sorry.
The first bullet point. I'm just wondering what's the zero state for.
This is 0.
Is it like an ancilla qubit or something?
Yeah, it's just one ancilla qubit. Just cat 0 times cat b. 0, just one qubit.
Okay, cool. Thank you.
Thanks.
Hello. Yeah. So thanks for the talk. So I have a question about why doesn't the dequantization technique work here? Can you just get a sketching of a B and get a...
Sorry, where are you? I can't see you.
Oh, here. Hello.
Oh, okay, great.
Yeah. So the question is, why doesn't the dequantization technique work here for the communication case? Can you get a sketching of B and get a very classical communication protocol for this linear problem?
Sorry, can you repeat your question? I didn't get it.
Yeah. So at the start, you said that for your communication case is different from the computation case where you can do dequantization by doing some sketching technique. So I'm wondering what's the difference here? Like, why doesn't the sketching technique work here for the communication case?
In the communication case, I think. When you study the time and complexity, classically you can use this the TANS technique, this sampling and sketching technique to find some efficient classical algorithms. But in the communication case, actually these techniques are not working anymore. I guess that's the reason why there is you cannot propose efficient dequantized algorithms or maybe protocols.
But can you just get a sketching of B and that should work? No? Okay.
I guess it's quite hard to get that since in our result you can prove some law bound. So basically, I guess this means it's quite hard to do that.
Okay.
Yeah.
Hi, very nice talk. So I have a question, just this page. That's very nice. So you show there's a quantum law bound for kappa square, right?
Oh, you mean this one?
Yeah. But at the same time, you got the classical upper bound, M, right? I mean, it looks like kappa can be really big, right? I mean, sometimes kappa can be
true.
square.
Yeah, you're right.
So in that case, why classical upper bound can be better than...
I guess... I just simplify the notation. Of course, you can say if kappa is too large, kappa square is larger than m. You don't need to use this protocol. I just.
I see. So they sort of implicitly.
When kappa is large, you can just use some simple protocol to do this.
Thanks.
There's maybe one more quick question. If not, maybe we can ask any more questions during the break. And let's thank Changpeng again.
Thanks.